So let's start today's class. It's going to be a continuation of logical instructions which we did last time. Last time we saw AND, OR, exclusive or, not, negate and test. Now today we are going to see about the shift and rotate instructions. Shift, what it does is moves the numbers to the left or right within a register or a memory location. Okay, this is what the shift instruction would do. Okay, so the shifting also can be used for simple arithmetic and as multiplication by the powers of 2 to the power of n, or division by the powers of 2 to the power of minus n. This we will see through an example. It will be very clear. The microprocessor instruction set contains 4 different shifts. There are 4 different shift operations. 2 are logical shift, shift logical left and shift logical right. And then there are 2 arithmetic shifts, shift arithmetic left and shift arithmetic right. So we're going to see all 4 of them one by one. Okay, and now let's see what is the difference between a logical shift and an arithmetic shift. Okay, when we tell logical shift, it means whenever we shift, say for in this example we are shifting towards the right, so the MSB, okay, the data of the MSB will go into the next significant bit. So whatever empty space is there in MSB, a 0 will be pushed in. So that is known as a logical shift. Whereas an arithmetic shift means whenever we are shifting it to the right, okay, so whatever was the previous MSB, the same thing will be held there. Okay, if it were a 0, it would be 0 again, and if it is a 1, it will be a 1 there. Essentially the sign will be preserved, the sign of the bit will be preserved. Okay, when we are shifting towards the right, in that case, whether it is arithmetic or logical, a 0 only will be put into the LSB positions in that case. Okay, so in that case, it doesn't make a sense in arithmetic shift if you repeat the same number of the LSB. So in that case it will be 0 always. Okay, only when we are moving from left to right in the MSB position, for a logical shift a 0 will be pushed in. For an arithmetic shift, whatever was there in the MSB, the same thing will be repeated there. So that is the difference between a logical and arithmetic shift, right? Okay, shift left instruction. So here this is what happens. Okay, so all the data will be shifted towards the left by 1 bit, and whatever is available in the carry in the MSB, that will be pushed into the carry flag. Okay, so this is what happens when we write an instruction shift. Okay, so this is the format for shift left. You can write a shift register. Okay, you can specify which register you want. It could be an AL, AX, BL, BX, whatever. Okay, and then you can write immediate 8. Okay, immediate. Okay, and then you can specify an 8-bit data out here, right? Immediate 8-bit data means by how many bits it has to shift. Okay, if I write shift AL1, the data will be shifted by 1 bit. If I write shift BL4, the BL register, it will get shifted 4 times. Okay, 4 bits will be shifted towards the left. Okay, and whatever is if the carry flag has already got some content, so that will be thrown out, and the new whatever data is available in the MSB, that would come into the carry flag. Okay, so after the instruction, the carry flag will have whatever is the data which was available in the MSB. Okay, max value of will be 8-bit. Whatever is the maximum, 254, right? No, 255. So that will be the maximum data. Okay, what is this used for? Okay, so we'll see that what it is used for. It can be used for an immediate for some easy multiplications, for divisions. When we it can be also used for division of a frequency also. Suppose you put all 0 0 0 zeros here and you put only one out here, right? And then you take the output from one of the bits. Okay, you are pushing it into the input output port. Okay, so what would happen is suppose this is running at 5 megahertz and you have an 8 bits and you have put an all zeros and 1 ones. So it will keep rotating like this, and 1 will come here after 8 clock cycle. So you get and 5 megahertz divided by 8 clock frequency. Okay, or if you put 0 1 0 1 0 1 0 1 here everywhere and then you keep rotating it, then you will get an 2.5 megahertz clock you will get. Okay, whereas you can use these shift registers also for controlling DC motors. We'll see those examples later on. In the lab, I guess there is one experiment on DC motors, so I would be explaining how those servo motors would work and how to control using these shift registers, the direction of the servo motors and things like that. So these are some of the utilities of these kind of shift operations. Okay. If the value of the immediate is more than it, then it essentially clear the yeah, if it is more than 8, it will push 0. It will put all zeros there. Correct, Ruben. Yeah, all if you put more than 8, it will be all zeros here, right? And when you're pushing it from this side, and if it is an arithmetic instruction, then it will become all zeros or 1 depending on the MSBs. Okay. So what is fast multiplication? Here if you see this is equivalent to binary 5. So if you push it by 1 towards the left, now what is the data available? It is 10. Right? What is 10? 5 into 2 to the power of 1. Now if you push it one more time, it will become 20. Like so, that is into 2 to the power of 4. So these kind of fast multiplication also can be done by doing the shift operation. Right? This takes much more, lesser time than the conventional multiplication algorithm. Okay, is this multiplication thing clear to all of you? It's pretty easy, right? If you have to shift it left, it is multiplication by by 2 to the power of 1. If you shift it by 2, it will be 2 to the power of 2. So accordingly, if you keep shifting it, it will be 2 by n times. It will be multiplication by 2 to the power of n. Right? So this is known as fast multiplication. Okay, and then you have something known as shift right. In this again everything will be shifted towards the right. So whatever was the contents of the LSB that gets into the carry flag. Okay, so that is known as shift right instruction. You can write like move DL80, right? So this is going to move it so many times into this side, right? And then this is the data which is pushed into the DL, and then shift 1, it will move it. Then you will get the result will be 40, because it is going to divide now. If once the data is moved towards the right, it is equivalent to dividing it. Okay, if you shift it by 2 times, it will become 40. Right? If you see the binary bits, so the result will be 40. Right? So this shift right can also be used as a divide operation. Now you have something known as the shift arithmetic left and shift arithmetic right. Right? Okay. In the shift arithmetic right operation, if you see, this data will be the same data will be preserved here. Rest of the data will be shifted towards right, and whatever is the LSB data, that will go into the carry flag. So this is known as the shift arithmetic left operation. It preserves the numbers sign. Okay, so if you see, if it is minus 80, once you shift it, do an arithmetic shift, it will be minus 40, and again if you shift it once more, it will become minus 10. So that sign will be preserved. So this will be always will remain 1 in case if it is a 1 here. So that is known as shift arithmetic right operation. Now this is now after shift, now we have something known as rotate instruction. Okay, so in rotate, what happens is, like, if rotate now here, let me tell you something. Let shift arithmetic in the left operation. Okay, so this data will not be preserved. Okay, it will be a 0 will always be pushed in here, right? For the shift arithmetic right operation, this MSB will be preserved, whereas shift operating, it is written also here, I think it is identical to shift operating left. Okay, shift arithmetic left and shift logical left will remain same. Okay, so there is it's not that the LSB will be preserved, so that doesn't happen. Okay, rotate. Now the rotate instruction, what it does is, here if you can see it clearly here, what happens here, the MSB data will come to the LSB and these data are pushed here like this, right? So this can happen again. The format remains the same, rotate, right? And then you can give the count, or you can give an 8-bit data here. So those many times it will keep rotating here. So this highest bit data will go into the carry flag. Okay, so you have to be careful here. The carry flag doesn't get rotated here. It's not that the first whatever was the carry that is coming here. It is only within the register the data is getting rotated. Okay, and each time whatever is the MSB, that is going to come out here. Okay, along with the carry also there is a rotate, that is a different instruction. Okay, so this is what happens on a rotate instruction, rotate left, and this is rotate right, in which everything moves towards the right and the LSB comes into the MSB, and here from the LSB the data is pushed also to the carry flag. So whatever data is available here, this goes into two places. Once it goes to the carry flag and one comes to the MSB, everything gets rotated here. So this is rotate right. Okay, and you have this is an example of rotate. Okay, so we can use the CL register. Okay, also we can use the CL register to put the count. Okay, if it is when we say rotate for 86, and you can write only rotate 1. If you want to rotate it more than 1 times, then you have to put the register into the number of times you want to register into CL register. Okay, and then you can write rotate AX CL. Okay, you can't write like it says in 803886 onwards, you can give a count which is greater than 1, but for 8086 you can't specify the count directly, but you can give any count up to 255 through a CL register. So you need to put the data into the CL. So rotate AX CL means it will rotate, like if you have written move CL 4 and then you write rotate AX CL, it will rotate the contents by 4 times. Okay, so this is rotate byte when you are specifying a memory location. So whether the word needs to be rotated or the byte needs to be rotated, that needs to be specified, and then 1 indicates that it is going to rotate it by 1 bit. Okay, here again byte PTR. So the contents of SI register, not contents of SI, the memory location indicated by SI, that byte will be rotated by 4 times because you have put 4 in the CL, right? Similar, this is for 80386 where the 32-bit is being rotated. So now there is this is an example where suppose you want to swap the data on BX register, and the data of AL you want to swap it to BL you want to swap it with BH. Okay, so BH data goes to BL and BL data has to comes to BH. So what you can do is you can move CL08 and then rotate it BX CL. So if you do this, it will rotate it by 8 bits, so all the data automatically which is available in BL will come to BX, and whatever data is available in BX will come to you can also do the same thing by rotating it towards the right. Okay, so you can use these two commands to swap the data between BL and BH. Yeah. Why is that in SHL we can give count directly but not in ROL? So I'm not very clear about that, and that's instruction set, and they could be something. So I'll have to see that instruction set in okay. Next class maybe I'll try to clarify that aspect. Okay, rotate through carry. Okay, so this is another instruction where I said along with the carry it gets rotated. So if this is 8-bit and then carry you can consider it as the significant bit here. Along with this is going to get rotated like this. So this is rotate carry left instruction. Okay, so now the carry flag also becomes the part of the rotation here, out here like this. So this is the difference between the rotate without carry, ROL and RCL. So here the carry also gets affected here with each. Similarly, you have rotate carry right. In this again everything from the least significant it goes to the carry, and from the carry it is going to come to the most significant bit. So this is the rotate carry right instruction.